Okay, so the last topic we're going to cover, um, the last thermodynamic topic we're going to cover in this course is some actual, well, some more practical cycles for that your real devices are based upon, right? For um, typical vapor, your typical steam power plant runs on a variation of the ideal Rankine cycle. Okay, this is the simplest form of the cycle that would power a traditional steam power plant. Okay, and the other thing we're going to cover is the vapor compression refrigeration cycle, which is essentially a reversed Rankine cycle, but modified slightly. And this serves as the basis upon which your air conditioner is operated upon. Like the air conditioner in your car is very closely operates on a cycle that very closely resembles the ideal vapor compression refrigeration cycle. All right. So I'm just going to basically introduce the two cycles and then flesh it out through a series of examples. Okay. So the cycle itself for the ideal Rankine cycle consists of these four devices operated in series. Okay. State one um, is a saturated liquid. Okay. What that means is the quality is zero. All right. That's what that should mean. If you see saturated liquid, you automatically understand that what that means is that the quality is zero. The cycle operates between two pressures. It operates between a low pressure and a high pressure side. Okay. So state one is on the low pressure side and its quality is zero. It gets compressed in the pump. It accepts input work, gets compressed in the pump, and at state two, it is at the high pressure, and it does so in an adiabatic and reversible way. This is the assumption. Okay. Um, I'm going to touch briefly on the differences between real devices and this ideal cycle, just briefly at the end, um, maybe through the examples. But basically, the assumption that we're going to have is that the pump is adiabatic, meaning no heat transfer, and it's reversible. So, like we discussed previously, that means that the entropy remains constant in the fluid. All right. So now this state is completely fixed because it has two independent intrinsic properties, right? I know the quality and I know the pressure. So I know the state at state one. I know that the entropy at state two is the same as it was at state one, and I have ideally I'd have the pressure specified or something like that. So state one is completely identified. State two, depending on how the problem's worded, may or may not be completely fixed, but you'll have enough information to determine the state two completely. All right, with the understanding that the entropy is the same as it was at state one, and then the pressure is the same as it'll be constant pressure as it passes through the boiler. Which leads me to my second point: the pressure at states two and three are going to be the same. As this heat is added, it does so at constant pressure. Okay, in the boiler. Then again, the turbine is adiabatic and reversible, so that means that the entropy is not changing through the turbine. And then the condenser again operates at constant pressure, and this time at the low pressure. Okay, and so just think about what this means. In order to reject heat, the condenser's got to be hotter than the atmosphere, or the medium in which it's rejecting the heat to, and then the the environment around the boiler's got to be hotter than the temperature of the boiler itself. So the choice of working fluid is kind of important. You have to tune your working fluid so that they operate in the conditions that that you need to operate in. Usually, and water is a really good one. So that's why it's been used universally. Well, pretty much universally. Um, Again, just like we actually discussed this in a previous example that we did during a Zoom meeting, but we're going to assume in all four of these processes that the kinetic and potential energy in the working fluid is negligible compared to the heat and work um, interactions. All right, and also we're going to assume that these are operating under steady state conditions. So under those two assumptions, which I guess is three assumptions, kinetic energy is negligible. The changes in kinetic energy are negligible. Changes in potential energy are negligible, and we're operating under steady conditions. The the energy balance for the four individual components simplifies to the work or heat interaction is equal to the mass flow rate times the change in entropy as the fluid passes, or I'm sorry, enthalpy, the change in enthalpy as the fluid passes through the device. So each one of them simplify into a very simple equation like that. And then so we can define the thermal efficiency in terms of only the differences in enthalpies as they proceed through the device. Like we went over how to get from here to here previously, and then so the ratio in heats is given just by the ratio of the differences in enthalpy between the two devices. Okay, so I can rewrite if I can solve for the four states, I know everything about the system. And so to solve for the four states, all I really need are the two pressures indicated. I understand that this point is going to be at quality of 0, and then I just need I need one other piece of information or something like that. So I need one, two, I need three numbers to specify all this stuff. I either, you follow what I'm saying? So I either need the two pressures and some other number specifying maybe the temperature at state 3 in order to fix the state over here. You'll see what I mean when we start doing examples, but so I can specify all this stuff by just stating three numbers is the point. As long as they're the right three numbers, I suppose. And then so this is essentially the same process in reverse, with the exception that I've discarded the pump for an expansion valve. All right. So everything is reversed. See all the arrows? I come out, I input work on this side. All the arrows are reversed. Now I'm rejecting heat to the hot side. I've gotten rid of the pump. That's just usually for practical reasons or monetary reasons. I could have put a turbine here and extracted some work, and my device would actually be more efficient. But the the cost of a turbine versus the cost of an expansion valve makes this a much more practical situation in most cases. Maybe some high-end refrigeration systems. I remember certain airplanes they expand things in turbine. Um, so it's not completely unheard of, but for your typical refrigerator and definitely for the air conditioner in your car, the use of an expansion valve gets the job done at a much lower cost. Anyway, so again, um, the cycle operates between two pressures, and state 1 is, in this case, it's a saturated vapor at uh, at the low pressure. So it's saturated vapor, and that should mean that keyword is just a code for the fact that the quality is going to be 1. All right, it gets compressed. The compressor, just like we just discussed, is adiabatic and reversible, which means that the entropy stays constant between states 1 and 2. The condenser rejects heat at constant pressure, So that means that the pressure at state 2 equals the pressure at state 3 equals the high pressure. Okay. Then it gets processed through an expansion valve. And if you remember, under the typical assumptions inside of an expansion valve, the um, the energy balance just simplifies to the fact that the enthalpies remain constant. So this is a really simple situation because enthalpy does not change from state 3 to state 4. The pressure changes, right? This is just, it goes from the high pressure to the low pressure, but the enthalpy doesn't change. And there's no work or heat interaction in the expansion valve. Um, Now, and then the evaporator accepts heat at um, at the low pressure, and then the cycle continues. Again, all the processes are steady. The changes in the kinetic and potential energy of the working fluid are negligible. And under those situations, I only have three quantities to work with: the input work, the heat rejection at the hot side, and the heat absorption at the cold side. And so the measurement of efficiency of a refrigerator, if you remember, is just the heat being accepted. What we're after is the heat being accepted on the cold side, and what it costs us is the work input. So you got the desired quantity over the cost, and that simplifies to just the changes in enthalpy um, as shown here. And then likewise for a heat pump, now I'm interested more in the heat being rejected to the hot side. I'm using this device to heat some room or something like that. And so it's the same thing, except this quantity on the top goes from being the heat accepted on the cold side to the heat rejected at the hot side. Same thing. Okay.